For our multiple linear regression model, we evaluated model performance using predicted mean squared error. For logistic regression, we could use the AUC or we could use prediction error. The prediction error, R of D, measures how well a model predicts the response value for a future observation. After the model or classifier is constructed, the subjects in the training data set, also called the learning data set, denoted by script L, are run through the classifier. The proportion of misclassified observations is the resubstitution estimate. The resubstitution estimate of our multivariable logistic regression model, also called our decision rule D, is denoted by R hat of D and is given by this equation. In many cases, such as our heart disease data set, we may not have an independent test set to use for calculating prediction error for use in identifying an optimal lambda. However, if we use the training data that we use to fit the model to also estimate error, that is called the resubstitution error because the error is computed using the same data used to construct the model. All classification procedures, including logistic regression, either directly or indirectly, attempt to minimize prediction error. Using the resubstitution error as an estimate of prediction error can give overly optimistic picture of the accuracy of our model. If possible, an independent data set can be collected for estimating error associated with the model derived using the training data set. In actual practice, only the data in the training set are available with little prospect of getting additional large sample to serve as an independent test set. The test set can instead be a random subsample of the training set. Operationally, select a fixed number of cases N1 at random from the training set to form the learning set denoted by script L sub 1. The remaining N2 observations form the test set denoted by script L sub 2. Only the N1 observations in the learning set are used in constructing the classifier D of X. Then the N2 cases in the test set are used to estimate prediction error. The estimate is given by this equation. Typically, the test set is 1/3 of the training set. The test set estimates of prediction error are unbiased, but the test set approach has the drawback that it reduces the effective sample size because only 2/3 of the data are used in constructing the classifier. If you need to estimate prediction error more precisely, you will need to have a very large sample size, as demonstrated in this sample size calculation. V-fold cross-validation is preferred for smaller samples. In V-fold cross-validation, the training set is divided by random selection into V subsets, each containing approximately the same number of cases. The V learning sample consists of all observations except for those in the V subset, so that script LV contains the V minus 1 divided by V of all observations. Usually V is taken to be 10, so each learning sample includes 9/10 of the cases. For each V, we fit the model using the learning sample, which is all observations not in L sub V, and let dV of X be the resulting model. Then, because none of the observations in L sub V were used in the construction for that model, this serves as a test set estimate for prediction error, given by this equation. For the large value V, each of the V models is constructed using a learning sample of this sample size, which is nearly as large as the original training data set. The basic assumption of cross-validation is that the procedure is stable. That is, each of the V models is developed using almost all of the observations in the training set such that their misclassification rates are approximately equal to R of D. Guided by this heuristic, the V-fold cross-validation estimate is given by this equation, which is simply an average of the test set errors over the V-folds. The R package bootstrap includes a cross-validation function. It requires that you create a function for fitting the model. Here we create a function that will fit a ridge-penalized logistic regression model. It also requires that you create a function for extracting the model predictions. As a reminder, when we predict a GLM net fitted logistic regression model, specifying type equals response in the predict function yields the probabilities. Also, as a reminder, GLMNet fits a penalized model for several values of lambda, and we want to evaluate model performance for each lambda, so we put our cross-validation call in a for loop. But to ensure we get the same random partition of subjects for each lambda that we evaluate, we set the random seed. In the end, this ridge.cv object has performed cross-validation for each lambda. Here you see the length of the first lambda in the ridge cross-validation result, stored in cv.fit, is 462. This is the number of observations in the heart data frame because the cv.fit entry stores the predicted probabilities. If we want to compare each lambda with respect to the area under the curve, we need to extract the area under the curve for each lambda. The 94th model has the largest AUC corresponding to a lambda of 0.031. The estimated coefficients corresponding to that model attaining the maximum AUC are listed here. Suppose instead of using the maximum AUC from the cross-validation procedure to select lambda, we want to select the lambda that minimizes prediction error, where the threshold used for calling an observation CHD versus not CHD is selected using Youden's index. Within the for loop, we first estimate the receiver operating characteristic curve. Then we identify the threshold using Youden's index. Using that threshold, we predict each subject as CHD versus not CHD. Errors are those observations for which the predicted class does not equal the true class. Summing those errors and dividing by the sample size yields the error rate. In this case, the 67th value of lambda minimized the prediction error, where the threshold used for calling an observation CHD versus not CHD was selected using Youden's index. That corresponding value of lambda is 0.38. The estimated coefficients corresponding to that model attaining the minimum prediction error are listed here. N-fold cross-validation is also called leave one out cross-validation. In this case, each observation is set aside and the model is developed using the other n-1 observations. Then, the observation that was set aside is used as a single test set sample, and error is estimated. Error is then estimated overall using this equation. If you have heard of jackknife estimate of prediction error, it is not the same as leave one out cross-validation, though there is little difference between the two estimates. Also, cross-validation can leverage parallel processors because the training and testing for each fold is independent. When performing n-fold cross-validation, the only part of the code that differs is the n-group parameter in the cross-val function changes from the value v, which was previously 10, to n, the sample size, which is 462 for the heart data frame. Afterwards, the cross-validation results need to be processed to either minimize prediction error or maximize the area under the curve. Here are some additional references.